Okay, this is the lecture video for MAC1114 Trigonometry. We're in section 7.4, and in this section we are going to be making use of all of the identities that you have learned in previous sections. As you can see, they've all been listed for you here again. These were introduced back in chapter 6. And then we have continued to use them through chapter 7 and we'll be using them for the entire course. So we have our quotient identities. And now keep in mind that the basic building blocks of all these identities are sine and cosine. So we cannot rewrite those two, but those two functions are used to produce all of the identities that you're seeing here. For instance, tan, if you recall, these two quotient identities is sine over cosine. Cotan is cosine over sine, the reciprocal of this definition. And some of these trig functions, there's more than one way to rewrite them depending on which identities you're using. There is another way to write tan, there's another way to write cotan. But when you're asked to write tan and cotan in terms of sine and cosine, these are the definitions. They're called the quotient identities. There are also the reciprocal identities. And as mentioned, there is two other ways to write tan and cotan. Like for instance, cotan is the reciprocal of tan. So you can write it as 1 over tan. Likewise, the tan function can be written as 1 over its reciprocal. It is reciprocal to cotan. So these are just two other ways that you can write the tan and the cotan function. You can write them like this, using the quotient identities in terms of sine and cosine, using sine and cosine. But you can also write cotan like this, and you can also write tan like this. It'll be dependent on the particular problem that you're working on. Cosecant is the reciprocal of sine, so it can be written like this, 1 over sine. Secant can be written as 1 over cosine. And as I said, we've been using these since section 6.2, so we're just going to continue using them. I will tell you this, one of the common mistakes when students are trying to simplify trigonometric expressions by substituting these definitions in for something that they're trying to simplify. Sometimes students accidentally missing what's going on here. They revert back to those definitions that were made out of X's, Y's, and R's. You are not to use those here. Everything that you substitute for one trigonometric function to another, they have to be in terms of the actual words that you're seeing here. So these must be memorized. Okay. So I gave you cosecant, 1 over sine, secant here, and then two alternative ways to write cotan and tan as opposed to these two ways. These are called the reciprocal identities because they're all written in terms of 1 over the reciprocal function. These are the Pythagorean identities, which we have used heavily thus far. One form of the Pythagorean identity is sine squared plus cosine squared is equal to 1. These two identities are actually equivalent to this original one, sine squared plus cosine squared equal to 1. They are derived from that. I would suggest us memorizing each of these three identities. Tan squared plus 1. This one goes cotan squared plus 1. And this is equal to secant squared, whereas this one's equal to cosecant squared. Maybe you can remember that this one, every function in here starts with a c, so you don't get it mixed up with this one. All right, then there were the even-odd identities, which were used to rewrite trig functions in a simpler form, and also when we were graphing. And as stated, there's only a couple of even functions here. Those are the ones where if they do give you a negative argument, you can just disregard it, because whether you evaluate the cosine at some negative value or whether you evaluate cosine at that same value but in its positive form, you will get the same answer. So when that is the case, and it is the case with cosine and its reciprocal cousin, these are the even functions that we've been working with. They are the only two even functions, cosine and it's reciprocal. Whereas these and these, sine and cosecant, tan and cotan, those are odd. And when they're odd, if you remember that negative cannot just be disregarded, that negative gets floated out and becomes the coefficient. You can see that happening here as well as here. So just a little review of all the identities that we've been working with throughout chapters 6 and 7, and we're going to be using them for all the problems in this section. Okay, you are also, in addition to trying to simplify trigonometric functions, by plugging in one or more of these identities and then simplifying it algebraically, you're also going to be proving that two expressions are identical. And so that's what this definition is about right here. You have proven that two expressions are identical when you get the exact same terms on one side as you have on the other side. You're going to bring it all the way to that point. Don't skip over any steps. These are just some general guidelines for doing that. When you do establish an identity, you're always going to start with the more complicated expression, and it'll be obvious pretty much all the time which one's more complicated. We're going to rewrite sums or differences of quotients always as a single quotient. So if you see two fractions, the point of that problem will the main point of that problem will be to bring the fractions together into a single quotient. You're going to be using all your algebra in here. Sometimes you're going to be foiling two trigonometric expressions. Sometimes you'll be factoring. Sometimes you'll be, working with quotients like this to bring them together into a common quotient. All of those things need to be done. We'll be distributing sometimes when working with these trigonometric expressions. All your algebraic techniques will be brought into the game here. And that'll be, more towards the middle and the end of the section. When you are trying to establish an identity, you are only to work on one side. And a lot of times, as the suggestion states here, that one side, it would be helpful to rewrite it in terms of sine and cosine. However, every different software that you work with to do your homework, they're going to have specific ways that they may want, steps that they want you to follow, and you will make sure to follow those. So although it is very helpful, oftentimes when you're establishing an identity to rewrite one side in terms of sine and cosine, you will follow the directions for the specific problem. And all that last step said is that what I've already verbalized, that last step on the previous page just said you're working one side until you bring it all the way to equivalency of the other side. In other words, you're working on one side until both sides match, if you want to put it in non-mathematical terms. Okay, so they're going to ease you into what you're going to actually be, when you're actually going to be proving an identity, just by getting you first to recognize things that you can substitute in for other things, for other expressions, and how to simplify them. Okay, so let's begin with example 1. This says sine squared theta is equal to 1 minus cosine squared theta. Is that true or false? Well, if you're going to answer a question like this, then you have to remember the basic identity on the previous page. It's a Pythagorean identity that goes like this. Okay, that's what it looks like in its original form. That's how it appears on the table previous page. Now, can it be made to look like this through simple algebraic manipulations? Well, let's see. They have sine squared by itself. What would happen if you took the original function and got sine squared by itself? You'd have to subtract cosine squared here, which you can just show with an arrow if you want. You can just go that you're bringing it over here, and that's why it changes sign. It's the same thing as subtracting cosine squared on both sides. So If you were to attempt to get sine squared by itself as they have it, would you get the same thing that they're claiming you get? And you can see that you do. So when they say, is this statement true or false? It is true. Okay, example 2. State whether the following statement is true and false. Now they're trying to get you to work with the even and odd identities. This first one was about the Pythagorean identities. So, you're going to see as I just go through a few problems that it is paramount that you memorize all of the functions at this point. You've been working with them for a while. And so at this point, you're going to have them because you need to be able to, on a test, pull out an identity automatically that is equivalent to another one. And that is super hard to do, almost impossible to do if you don't have them all memorized. So make sure you make flashcards, do whatever you have to do to memorize those identities. Okay, here it's the even and odd identities. So here one would have to know which ones are odd and which ones are even. When they're even, you can just get rid of the negative. If it's an even identity, those are cosine and sine. The even ones are cosine and secant. You can just get rid of the negative. But when it's an odd identity, which is everything else, so I'm not going to write them, all the other trig functions other than cosine and secant are odd functions. And with the odd functions, the negative can't just be erased. It floats out and becomes the coefficient. So you can simplify one of these sides. I'm going to simplify this one. This is odd. This is an odd function, and so that negative floats out and becomes the coefficient. And then this argument is no longer negative. This, on the other hand, is an even function. And for an even function, you can just disregard the negative to rewrite it in its positive form, to rewrite the argument in its positive form. So, did you actually get on this side what it says on this side? And you can see that this is exactly the same. Order doesn't matter. Just because the cosine term here is first, but it's second here, that doesn't matter. Are they the same trigonometric functions, and do they have the same sign in front of them? And they do. This sine term is negative, so is this one. This cosine term is positive, so is this one. So these are identical. So when they said that this is equivalent to this, through simplification, we have proven that to ourselves. Okay, then we're going to example 3. Complete the following equation. Tan squared minus secant squared is equal to what? Okay, so in this particular problem, I'm going to rewrite everything. They don't give you specific instructions as to how to go about simplifying it, because sometimes they want you to go in a specific order. But in this problem, you don't have that, so I'm going to take everything, I'm going to rewrite everything in terms of sine and cosine. And that was one of the guidelines for simplifying. That oftentimes just writing things in terms of sine and cosine will get you to the most simplified version of the expression. So tan squared, well, tan is equal to sine over cosine. So when you take what's equal to tan and square it, and we'll put the theta in, and I guess I'll just squeeze it right in here. You get sine squared and cosine squared. The square goes on the trig word, not on the theta. So right here we'd have sine squared theta over cosine squared theta. Then when you do the same thing to secant, you get 1 over cosine squared, because secant is 1 over cosine, but in its squared form it's 1 over cosine squared. Okay, then one of the guidelines on the previous page said that whenever you have the opportunity to take two quotients, two fractions, and rewrite them as a single quotient, that you are to do that. That is considered simplifying it. So if we were to pull these together, what's required to pull two fractions together is that they have a common denominator, and they do. So I'm going to pull these together. I'm going to pull the tops together. And when you pull the bottoms together, all you do is rename that common denominator. You don't do any more arithmetic there. Once the denominators are the same, and these were the same as soon as we renamed them in terms of sine and cosine. So now I have this. The only thing that I want to question at this point is there something that I could replace? And this is mostly what this section is going to be about. Substitution, substituting a more complicated expression for a simpler one so that you can continue simplifying. Like right now, there is nothing that I could cancel out here. But if I substitute something in here that's equivalent to sine squared minus 1, and then it happens to reduce with cosine squared, then it gives me a way to simplify. So substitution and algebra. You're going to go back and forth between those two. Sometimes you'll be doing the algebra first and then the substitution. Sometimes you'll substitute, then do the algebra. So far I have done substitution for sine squared. I substituted it with its alternative name, sine over cosine, but in the squared form it was sine squared over cosine squared. I substituted for secant squared, 1 over cosine squared. I did some algebra, bringing two quotients together as a single quotient, and now I'm going to substitute something that's equivalent to sine squared minus 1. Okay, that has to do with the Pythagorean identities. Up at the top of the page in number 1, we already have the Pythagorean identity that concerned sine squared. Because when you see things in their squared form, almost every time they're talking about it's a Pythagorean identity that's going to allow you to go further with that. In other words, substitute something for it. So this is what the Pythagorean identity that contains the word sine squared, which is what we're working with in this problem, is this. Sine squared plus cosine squared. How is equal to 1. So how can you take that and make it look like this? Because only if you can make one side or the other, either the left side or the right side, look like this, will you be able to substitute. So let's think about that. All right, so let's say I'm just going to do some work over here to the side. I'm going to just leave the thetas out for the time being. I can put them back in when I bring it over here. So sine squared plus cosine squared is equal to 1. I want either this side or this side to look like this. So if I was to bring the 1 over here, I would have sine squared minus 1, but then the cosine squared would still be on the same side. I just want sine squared minus 1, just an expression that says exactly what this says. So I'd have to move this over here. And the minute that the cosine squared gets moved over here, it switches signs. Just like the 1 switched signs when it, because basically what you're doing with these arrows, you're going minus 1, minus 1. And then cosine squared, same thing. You're subtracting from both sides and bringing it to the other side where it appears as a negative. So I now know that cosine squared is equal to sine squared minus 1, and therefore I may substitute one for the other. When two quantities are equal, that is the basis of substitution. It allows you to perform the substitution. So here I go, continuing with this problem. I'm going to substitute for sine squared minus 1. Right in there, I'm going to substitute its equivalent, which is negative cosine squared. And by doing this substitution, and then copying what I had on the bottom all along, I can give a much more simplified answer than what I had at this stage. This stage, I had two different trig functions, a fraction. I now am going to have no fraction and no trig functions because cosine squared over cosine squared is 1. But because of the negative that you see there, it is -1. So, in its most simplified form, there is the answer to that problem. Okay, so this was the final answer, which came from this step right here. Okay, moving to example 4. Decide whether the following statement is true or false. This has to do with even and odd functions again. I just went over the even and odd functions on the previous page as well as this one. This is an odd function. Therefore, this negative comes out and becomes a coefficient. And at that point, you've made the argument positive. So I used an odd property on this first term. The second term, I'm just going to copy it. And they want to know if what's on the left side is actually equal to 0. They claim that this is equal to 0. And by simplifying it, I can see that that is true. Negative sine theta plus positive sine theta cancels. And you end up getting 0 on each side. So that is, in fact, true. Okay, example 5. Determine whether the statement below is true or false. In establishing identity, it is often easiest to just multiply both sides by a well-known non-zero expression involving a variable. Never multiply both sides by a variable because you only want to do substitution of two things that are equivalent. That's the most you're allowed to do. You're not solving an equation, therefore you may not use the properties of equations. Like you'll see some students and they'll have terms on the left, terms on the right, and they'll start moving things from left to right. Well, you're allowed to do that if someone tells you that it's an equation. If you were starting off knowing that it was identical on both sides, that's what an equation is. Then you could use the properties of equations, moving things from side to side by subtracting from both sides or adding to both sides. But you're not being given an equation in these problems. The problem will actually say, show that it's an identity. You're proving that that you have identical expressions, and in plenty of them you won't have identical expressions, and therefore you do not have the right to use the properties of equations. Another thing that you can't do for both sides is, and I see students doing this too, which is why it's a question, you can't multiply both sides by a variable because that introduces answers that really are not answers to the problem. It gives extra answers because you've altered the original equation. So, like for instance, I can take you back to an algebra statement. Let's say you had an equation like this, and you think that you can multiply both sides by a variable. Well, if you start taking this original equation and multiplying both sides by a variable, you now have x squared is equal to 7x. When you started with this original equation in its original form, the only solution that this equation had when I first started before I used the extra variable is the only solution is 7. The minute you start multiplying both sides by a variable, you now have this x squared on this side, 7x on this side. And if you were to bring this to the other side and asked to solve it, you no longer have just one solution as you did with the original statement. The original statement was x equal to 7, already in its solved form, and the only solution it has is 7. You bring this extra variable in it, it becomes x squared equal to 7x. So if you then went and solved that, you would see, look, there's extra answers now. because to solve this, you'd have to factor it. You now have answers, the way that you get the answers is take each of these factors, set it equal to 0, and you now have x equal to 0 as an answer and x equal to 7. So do not multiply both sides by a variable. And that's what they're asking here. Is this true or false? Is it just easiest to multiply both sides? That's false. In fact, you're not allowed to do that. Okay, moving on to example 6. Okay. So for example 6, it says, which of the following equations is not an identity? Okay, so let's see. Practice showing that things are an identity. Tan on the left side would be sine over cosine. See, I'm pulling that definition right from memory. They're saying that that's equal to this. Well, they're only equal if they look exactly alike, and you can see that these do not. This has sine on the top while this has cosine on the top. So which one is not an identity? That's not an identity. This one right here, let's make sure that shouldn't be more than one answer the way they asked the question. This one right here, this is an odd function. Odd functions, that negative comes out and becomes the coefficient. This is an identity. Remember, the question is, which one is not an identity? We're looking for not an identity. This one is an identity, so that's not the answer. Cosecant. Cosecant is most definitely defined in its reciprocal form as 1 over sine, and they're claiming that it's equal to 1 over sine. So that is an identity. Write a little bit nicer so that it's actually legible. So this one is an identity as well. Okay, and then cotangent squared plus 1. Well, that's just flat out one of the Pythagorean identities. On the previous page, it goes 1 plus cotan squared plus 1. Just like the other one starts off tan squared plus 1, and this one ends with cosecant squared. So yes, this is an identity. It's one of the Pythagorean identities. Okay, so we picked the right one. It was the only one that wasn't an identity. Okay, example 7. Rewrite secant of theta over tan of theta in terms of sine and cosine. Okay, so I did that in example 3. This time it actually says to do that. I would revert back to that anytime that you don't have specific directions on how to start the simplification process. So here they're telling you to rewrite this. So secant is the reciprocal of cosine. So I'm using a reciprocal identity here. Tan is written, it can be written as two ways. It can be written as 1 over cotan, but then I bring two things into this. I think, I would love to have a definition for tan that actually has cosine in it, because then when I multiply by the reciprocal, something will cancel. So I opt to use this definition for tan, sine over cosine. So there it is. Anytime you have a complex fraction like this, you're going to simplify by just, instead of dividing, multiply by the reciprocal of the cosine, reciprocal of the divisor. And oftentimes I have just called that floating this to the top and flipping it over, float and flip. It's the same thing as multiplying by the reciprocal. You'll be using that a lot in this section, as we have in all sections. Cosines cancel. You're left with 1 over sine. And there is another name for this. Reciprocal of sine is also called the cosecant. And you'll have to just see, how far they want you to go. Sometimes there'll be further, instructions there. Sometimes they'll just let you leave it here. I mean, it is equal to cosecant. And if you're doing this for me on a test, I want you to go all the way to a single word rather than giving a definition, because in my mind, that is more simplified. And in fact, that's how I've seen it in many books. But the software, I notice, will sometimes let you stop short of that. So I believe this is the answer that they want for this. Okay, so example 8. Now we have cosine of theta minus sine of theta over a denominator of sine of theta. And I mean, just notice here that you have two different fractions. The denominators are different. The minute that you see that, remember that one of the guidelines on the first page when we reviewed all of the identities that you're going to be using for substitution purposes to help you simplify, that one of the guidelines said rewrite sums or differences of quotients, which is exactly what you're looking at in this problem, as a single quotient whenever you get the opportunity, because otherwise you will not be able to continue the simplification process. So it says rewrite these two quotients over a common denominator. Express your answer in terms of sine and cosine. So the easiest way to get a common denominator is just to throw in each of these denominators in the form of a product. And that will be the common denominator that you are going for. That means you want each of the denominators to look like this LCD. So you devise a common denominator, and then you try to transform each of the denominators, which is what this says. You want each denominator to look like the LCD. So you're going to transform each one into the LCD. So to make this one look like the LCD, you'd have to multiply the bottom by cosine, and therefore you'd have to multiply the top by cosine. But the top has two terms in it, so you're going to need to distribute that cosine to each of these terms. Okay, so that will make this denominator look like the LCD. Then look at the other denominator. And notice that in terms of looking like the LCD, it has the cosine but not the sine. So you'll have to multiply the bottom by sine to make it look like the LCD. And whatever you multiply the bottom by, you have to multiply the top by as well. So that in essence, what you're multiplying by for each of these fractions is 1. You're multiplying by cosine over cosine, that's 1. You're multiplying by sine over sine, that's 1. So you're not changing what it's equal to, just changing the form so that you can bring them into a common denominator. Okay, so let's see what we have here. When we bring this all together, and I'll do my work down here at the bottom, I would have cosine squared, and then I'll bring my final answer here. I'd have cosine squared, then cosine times sine with a negative in front of it would look like this. Just distributing now. You have a single term out in front of a parenthesis, that means distribute. Okay, so that's that. Both of these denominators, so I'm pulling them together into one fraction, which was the whole point of getting common denominators. Both of these denominators are sine times cosine. Okay, then this other one, I'm distributing sine into both of these terms that are in the parentheses. So it would be sine times sine, sine squared. And that is a positive in front. So it would be sine times sine with a positive applied, sine squared. Okay, then it would be sine times cosine with a positive applied, positive out here. Okay, so after I complete the algebra, distributing that cosine into each of these two terms and distributing the sine into each of these two terms, next thing I need to do is to look for like terms to either combine them or see if they cancel. So I see that I have a cosine times sine product here, cosine times sine product here. One of them's negative, one of them's positive. So these two terms cancel. That leaves me on the top with cosine squared plus sine squared is equal, oops, we have an equal sign there. This, all I had was this fraction. So cosine squared plus sine squared, and then on the bottom I have sine theta times cosine theta. Okay, so what is an even more simplistic version of this answer? Well, you simplify things by substituting one quantity, a simpler quantity, for a more complicated quantity, and I can do that right here. This is one of the Pythagorean identities, that there is something that is equivalent to this, and it goes like this. Sine squared plus cosine squared in its original form is equal to 1. So anytime you see sine squared plus cosine squared, which you see right here, that is equivalent to 1, and therefore you may substitute 1 in place of it. So this ends up being simplified into 1 over sine of theta times cosine of theta, and that's as far as you can go there. Okay, so that's what belongs right here. Okay, moving on to example 9. Okay, in example 9, it says factor and simplify. Type your answer in terms of sine and or cosine. Okay, so here you're going to have to do a form of factoring that a lot of students have a little bit of trouble with. It's a trinomial, but the leader is bigger than 1. So you can do this by the guess and check method if you're really good with your number combinations. If you're a little bit stronger in that area and if you need a little bit more help, which most students tend to need, is I would suggest splitting the middle term. I've demonstrated this in previous sections. I'm going to do it again. Now you could rewrite this as though it was an algebra expression, like instead of sine here in the middle, you could just say sine is equivalent to x to the first degree. Notice that this sine is to the first degree. This would be x squared because here you have sine to the second degree. But you can leave the trig words in. I mean, when you're factoring, you're really just working with the coefficients. So I'm going to leave the trig word in this time so we can get used to solving it as, simplifying and working with it as a trigonometric expression instead of an algebraic expression. But we are using those algebraic techniques. So I'm going to do some of my work up here. Okay, this is the splitting the middle term factoring method because they want you to factor. Okay, this particular factoring technique is for second degree trinomials. When the A value, that's that guy right there, that's A, this is B, this is C. Just like when you're doing quadratic formula, you have to identify A, B, and C, which are nothing more than these coefficients. So whenever you're using splitting the middle term is because you have a second degree trinomial, and your A value is greater than 1. Because if it's just a 1, it's easy enough to just do by a 2-step process. But here you're going to have like 4 steps. Okay, so here we go. Splitting the middle term starts like this. You're going to be looking for 2 numbers, just through knowledge of your times tables, that is equal to the A times C value, which in this case is 24. A value times C value is 24. The 2 numbers that you come up with here, and there are several, there's many that you could multiply together to get 24, but the 2 numbers that you decide upon as the factors of 24, you need to also be able to add them to get the B value, which is 10. So this came from A times C, this came from B. And in that case, you go from having several possibilities to just one possibility that can possibly work, and that would be the 6-4 combo. I mean, if all you were considering was step 1, there would be 6 times 4, 8 times 3, 12 times 1, and then there's other combinations with negatives. So if you're considering solving both of these simultaneously, which is what you're trying to do, it has to be positive 6 and positive 4. Only one combination will satisfy both steps. Once you come up with those 2 numbers, those are the numbers you're going to use to split the middle term, 10 sine theta. You're just going to rewrite it. So let's go after that. Okay, we're going to write the first term as is. We're going to write the middle term as 6 sine theta plus 4 sine theta. This is the variable right here. You're just giving it 2 different coefficients. You're splitting up that 10 into 6 plus 4. And there's your 10 sine theta, but split up into 2 numbers. And then there's that last term. Okay, let's just continue working on factoring this top. Okay, so when you split the middle term, you now take something that was 3 terms and you've stretched it out to 4 terms, which makes it subject to factor by grouping. So when you do factor by grouping here, you can go, and you can even rearrange these. If you think you're gonna, by rearranging them, it's gonna be easier to identify which ones, what the greatest common factor is, because we're going to do factor by grouping. And when you do factor by grouping, you're taking out the greatest common factor 3 times. So you're allowed to rearrange those 2 terms and put the 4 first. In fact, I think I'll do that. It's probably going to make it easier for you to see what the common factor is. Okay, so I still have my 10 sine theta in the middle. We're going to group 2 at a time to start off the factoring by grouping. So let's see, each of these has at least a 4 as part of its coefficient, and at least 1 sine theta term. So 4 sine theta is the largest, the greatest common factor for these 2 terms. You always put 1 parenthesis next to your GCF that you just pulled out and ask yourself, that times what would give me this first term back, and that would be 2 sine theta. That times that is the 8 sine squared theta. 4 sine theta times what would give me this term in the back, and that would just be 1. Now move to the back 2 terms and do the same thing. Take out a GCF for these 2 terms. Okay, both of these terms have at least a 3. So take out a 3. They don't both have a sign, so you can't take that out. And that GCF that you take out, it works as a multiplier to get back each of these terms. So 3 times what gives you that back? 2 sine theta. 3 times what gets you the back term? 1. Okay, we've taken out a GCF out twice. Here we go for our 3rd GCF. Now you look at these as 2 terms. This is 1 term. This is 1 term. And you're just asking yourself, what do these 2 terms have in common? You can see that 2 sine theta plus 1 belongs to both terms. So now it comes out as the 3rd common factor. 2 sine theta plus 1. And then what goes in the other factor to get this fully factored are the coefficients that you pulled out, the first two GCFs that you pulled out, 4 sine theta plus 3. 4 sine theta plus a 3. Okay, now this numerator, which gave us a little bit of a run for our money, it is fully factored. So I'm going to come back down here and finish it. This would be So this would be 2 sine theta plus 1 times 4 sine of theta plus 3. So that was a technique called splitting the middle term, and it is often used when you think the numbers, the coefficients are getting pretty big and you might have a hard time just coming up with them in your head. There's also the technique called guess and check. And some students will stick with that, but most students tend to move to splitting the middle term when these coefficients get a little bit bigger, because then there's a lot more possibilities. You might be able to work with guess and check on this bottom one. That's where you just guess at the coefficients when you're factoring, and then you check them by considering the foiling process. So I'm going to demonstrate that one as well. You do have options, which I guess is what makes factoring so difficult for students. Okay, so when you're doing guess and check, all you do is try to think of a way to break up this middle term. You know you're going to put one of the, because you're always trying to bring your factors down to first degree. So you definitely want to break up that sine squared. And you're going to have to give the 2 to one of these. So one of the sine thetas, I'll give the 2 to, and then the other sine theta will just have a 1 in front of it. Because you should be able to multiply. Now I'm reverting back to my knowledge of foiling, because foiling is how you check whether your factoring is coming out correctly. This times this should be that, it is. And then when you're going to fill out these back positions, it's a matter of how can I break that down? Because these are such small numbers, and because they're even better, they're prime numbers, there's not a lot of ways to break them up. And when you're in a situation like that is when students sometimes forego the splitting the middle term technique because the numbers are not big enough to warrant that, and they fall back to guess and check, it's called. It can go by different names, but it's all the same, the same thing. So when you're filling out these back positions, it's what number times what number would give you that. Okay, no choices other than 1 times 1. So nice number to have. When the last term is positive, that means both of these signs are going to be the same, and whatever is in front of the middle term is what they'll both be. Okay, so I have this all factored now. I used a technique of splitting the middle term for my second degree trinomial. I used the technique of guess and check to factor my bottom second degree trinomial. And I see that I have matching factors, which is only revealed once you get to the point where you have fully factored the top and the bottom. You don't see any of that when it's in its non-factored original form. These cross out, and your answer then becomes the pieces that are left over, the ones that didn't factor. So that would be 4 sine theta plus 3 at the top, and if you only have one expression on the top and one expression on the bottom, you can remove the parentheses, and that would be the answer that goes right in there. Okay, so getting into this simplification process and mixing it with all the algebra. Here we come into example 10, and this one says establish the identity. They're making you do it in a specific order, so pay attention to the directions. Okay, this one says write the left side in terms of sine and cosine. Okay, so here's my left side. I want to rewrite each of these in terms of sine and cosine. So This piece already says cosine. There's no rewriting that. That's one of the bare bones that makes up all the other definitions, the words sine and cosine. So leave that alone, as they have prompted you into. That's why they rewrote it for you, so you don't rewrite it. Cosecant can be written like this. One over sine. This is the reciprocal identity that's equivalent to cosecant. Okay, then it says take this result and write the result from the previous step right here as a single fraction. Well, cosine's the same thing as cosine over 1, and if you're going to bring two fractions together through multiplication, it's top times top, bottom times bottom. So here you would have cosine of theta over sine of theta. Okay, the fraction from the previous step then simplifies to cotangent. So they want to know what was the name of the kind of identities where that stated the fraction from the previous step, cosine over sine, simplifies to cotangent. Okay, and we can look at those on the first page. What was the name of the type of identity that was like this? Now, you know the reciprocal identities are all written as something is equal to 1 over. These were called the quotient identities. So if you look, at what I gave you on the first page, I can get back to that first page. Here it was. See, cotan can be written like this if you're using a reciprocal identity, but what we are looking at right now is this one. These are called the quotient identities. None of these are 1 over anything. Those are called the reciprocal identities. And the ones that have all the squares on them, those are called the Pythagorean identities. So this is a quotient identity. Okay, moving to number 11. In number 11, it says establish the identity. Now, we saw this happening in the last problem where you had a single term on the outside of a parenthesis. Whether that single term is in the back or in the front, single term times multiple terms in a parenthesis means distribute. So that's what you're going to be using here. Write the left side, all of this, in terms of sine and cosine. Okay, so if we're going to do exactly what they said, doing it the way, now the first thing you would probably be prompted into doing is distributive property if you were doing this without being told what to do first, what to do second, and so forth. So in compliance with these instructions, write the left side in terms of sine and cosine. Okay, well, this word you can't rewrite. It's as bare bones as it gets, but you can rewrite each of these. So cotan is equal to, write it in terms of sine and cosine. That means only use the words sine and cosine to rewrite it. No ones. So that stops you from rewriting that as 1 over tan. You're not to be using the number 1, just sine and cosine. So cotangent is cosine over sine. That's what you would fill in there. Plus tan is the reciprocal of that. Sine over cosine. So that's what they wanted in that particular blank spot or for that answer. Simplify the expression inside the parentheses from the previous step. So, and write the result in terms of sine and cosine. So if you're going to go simplify that particular fraction, they want you to bring it into one fraction and then simplify it. Okay, so I'm going to do my work right out here. First, I'm going to try and bring this into a common denominator. So I'll do a little bit of the work over here and then I'll finish it here. If I want these two to have a common denominator, then I need one of these, whatever's mentioned in the first denominator, times whatever's mentioned in the second denominator. That is what I want both of my denominators to look like. Now, in an attempt to make each of these denominators look like this, I provide it through multiplication with the missing term. So to make this look like this, it needs cosine. Whatever I multiply the bottom by, I have to multiply the top by. This denominator, in order to make it look like that, needs to be multiplied by sine on the top, sine on the bottom. Okay, so let's continue that work over here in the space that we have available. So cosine times cosine, and then we'll put the finished answer here after we get done simplifying it. Would be cosine squared, cosine times cosine, over that common denominator. So I'm just going to write once you get a common denominator, just write it once and pull both of your numerators together through addition or subtraction. So that common denominator is cosine times sine. It doesn't matter whether you write it as cosine times sine or sine times cosine, same thing. Second numerator is sine squared. Okay, so these are all simplification steps, taking two separate quotients and bringing them together by figuring out what the common denominator is into a single quotient. That's one thing. Then you can do more simplification here since they have asked you to simplify it. You simplify the expression inside. What other simplification can you do? You can do substitution. Besides doing the algebra that we just did where we came up with a common denominator, rewrote the two separate fractions as a single fraction with a common denominator, and then notice that up at the top you have something that you can substitute in for. Once again, Pythagorean theorem goes like this. One of the Pythagorean identities goes sine squared plus cosine squared is equal to 1. These two sides are equivalent, so if you ever see this expression, you're allowed to plug this in for it, and therefore you will have something more simplified. Okay, so after bringing them together as one fraction with a common denominator and also doing substitution using Pythagorean identities, I have come up with this. So that is what goes here. 1 over cosine times sine. Okay, you can work it off to the side and then bring your most simplified version of the work you're doing over into the answer blank. Simplify the expression from the previous step. Okay, so we're looking at this, what we got to by the time we simplified it as much as we could, and write the results in terms of sine. Well, cosine, which is this is being multiplied by cosine. Cosine is the same thing as cosine over 1. So you have a cosine in the numerator of this fraction being multiplied by another fraction where cosine's in the denominator. So, being that the cosines on two different levels, numerator and denominator, they cancel, and you're left with just 1 over sine times 1. And so that goes here. Okay, it says the fraction from the previous step then simplifies to cosecant using what property? If you were going to call this cosecant, you have to think about what definition on the previous page said that the reciprocal of sine is equal to the cosecant, the reciprocal identities. Those are called reciprocal identities anytime they are renaming something using a 1 over another function. Okay, that completes 11. Let's move to 12. Number 12, establish the identity. Here, what they're trying to get you to do, binomial times binomial, that's FOILing. There is a shortcut for this. Anytime you are multiplying two binomials, two terms, those are binomials, and they happen to be conjugates, there is a shortcut for that when multiplying conjugate binomials. Conjugates are just when you have two terms, and in both of these two-termed expressions, front terms are the same, back terms are the same, but the signs are different. Those are called conjugates. When multiplying conjugates, there's a shortcut. Instead of going through full-blown foiling, the shortcut is just to square the first term, square the back term, and you could either be looking at this binomial or this one. You don't need to look at both. Just square the front term, square the back term, and throw a minus that in between. That cuts out 3 of the steps in the foiling process. So let's do that. Okay, so just to get this foiling, we're going to do these 2 steps and put the minus in between them. So I'm just going to look right here as I do it. As I said, you can look at either one. So this term squared is cosecant squared. This term squared is 1. And then throw the minus sign in between them. So it says establish the identity. I did some of my work up here. It says multiply and write the left side as the difference of 2 squares. That's exactly what I did. This came about by squaring, this came about by squaring, and the minus makes it the difference of 2 squares. So let me put my answer right in here. Cosecant squared theta minus 1. Okay. The next question says, there's multiple questions here. So the expression from the previous step, this one right here, is equivalent to cotangent squared using what? Okay, so any of these things in their squared form have to do with the Pythagorean identity. I mean, this one in its original form looks like this. 1 plus cotan squared, and the other one starts off with 1 plus tan squared, the one that's similar to this, is equal to cosecant squared. I was trying to just give you a way to memorize this. Both of the trig terms here both start with C in one of the Pythagorean identities. So they're saying, what makes cosecant squared minus 1 equivalent to cotangent squared just by manipulating this? If you were to manipulate this, what makes it equivalent to just cotan squared? Well, imagine getting cotan squared by itself. All you'd have to do is move the 1 to the other side, and cotan squared is equivalent to cosecant squared minus 1. Once you move that, running out of room here. Once you move that 1 to the other side. Okay, so what makes them equivalent? The fact that this comes from, this being equivalent to this, or equal to this, comes from the fact of this Pythagorean identity. So that goes there. Moving to number 12. In problem number 12, no, let's see, that might have been number 12. That was 12. So this is number 13. Example 13, it says establish the identity. Write the left side in terms of sine and cosine. So that's all they want you to do right now. Just do it in the order that they're asking you for. So here's the left side. We're going to write each of these in terms of sine and cosine. So tan is defined as sine over cosine. Secant is defined as 1 over cosine. Simplify by writing the expression from the previous step, that's this, over a common denominator. So we've practiced this in a couple of problems so far. You're looking to get a common denominator unless they already have one. Now look, in this particular problem, they already have a common denominator, so you don't have to worry about making them the same or coming up with an LCD. You can just right away bring them into one single fraction. Okay, they've already provided the bottom of the fraction here. I used thetas, but there was actually u's in this problem. So let's just keep it consistent. Whatever they're giving you as the angle, just use that throughout the problem. So So this will be sine of u over cosine of u, and this one will be cosine of u. So now bring them into one fraction. They've already provided the common denominator. You're just going to pull these numerators together using the sign that connects the two fractions. So sine of u minus 1 will be the numerator, and the cosine of u is the denominator, which they already put there. Rewrite the expression from the previous step by multiplying the numerator and the denominator by sine of u plus 1. This technique that they're trying to get you to perform is something that's used multiplying by a conjugate. This is the conjugate of this. Same first term, same last term, but with different signs. So we'll definitely use our shortcut when we go to multiply. They're telling you to multiply the numerator and the denominator because you always have to do the same thing to both top and bottom in order for this to remain equivalent to what it is right now. So they're saying multiply. So you would give just that answer right in there, but then I'm going to do some of my work here so I can get the answer for the next one. So sine of u plus 1 is what they're asking us to multiply by. And therefore you have to multiply the bottom by sine of u plus 1 also. Okay, we're going to use that shortcut again. We have conjugates here, so it's just square minus square. That's the shortcut for getting all of that foiled out with a few less steps. Okay, you can either be looking at this one when you do square minus square, or you can be looking at this one. Doesn't matter. In the end, you need to put a minus in between your two squares. You should have the difference of squares as your product. Okay, so squaring this first term, sine squared, squaring the back term, 1, and then put that minus sign in between them. Okay, so we're at this point right now. They already did the bottom for you. They wrote cosine of u times sine of u plus 1. Okay, now it says that you should simplify your answer. So maybe I should have done that before actually delivering the answer right here. So let me continue my work off to the side, and then I can bring my simplified answer into this final space. So when I multiplied top and bottom by sine of u plus 1, it was sine squared u minus 1. That's what I got when I used my shortcut, square minus square. And then here I had, and actually I could have just left it the way it was instead of multiplying it out. See, they're kind of prompting you into steps that they want you to use rather than you going with your own intuition about what to do first, what to do second. I definitely would not have done it in this order, but with respect to what they want you to do here, they're trying to get you to simplify, and the only way that you're going to be able to simplify is if you take what you had up here at the top and just start canceling right now. So that's what I'm going to do. Instead of multiplying all of this out, let's just leave it the way it is in the previous step. So we'll go with what we had in the previous step and then just simplify right from there. Which again, you're going to be prompted to do certain algebra just organically. You're going to have that feeling to multiply these together, and on a test you would. You would just keep going based on, because some students will do it one way, some students are going to do it in a different order, but no one should be missing any steps. Here they want you to do it in this specific order, so going with what you have right now. You multiplied both the top and the bottom by sine of u plus 1. And if they want you to just show what simplifies, you can see that, let's see. Simplify your answer. Unless I guess they do want you to leave it like that. Okay, so they do want you to leave it like that. So simplify your answer, because I'm looking up here to see if anything cancels. But if I go and cancel that, you're going to be right back to where you started again. So let's just give this for an answer. Sine squared u minus 1. Leave that like that. And then it says write the numerator of the expression from the previous step in terms of cosine. Okay, so write the numerator from the previous step in terms of cosine. Okay, so we can use Pythagorean identities here. We can remember that sine squared plus cosine squared, you're probably going to always want to think of it in its original form first, is equal to 1. But we need, if we're going to do any kind of simplifying on this previous step on the numerator, we need one side of this equation, either the left or the right, to look like this, because then we can substitute and simplify. So they're wanting you to come up with another expression that you can plug in terms of that. So if I was to bring the 1 over here, I would have that sine squared u minus 1 that I see right here. But that's all you want on one side, is just that. So move this to the other side, which will be negative cosine squared u. And now we have two things that are equivalent, but that match what's going on in our particular problem, all by manipulating the original Pythagorean identity, sine squared plus cosine squared is equal to 1. So this negative cosine squared u can be substituted for this because they're equal, they're equivalent. So I'm going to come in here now and write negative cosine squared u over cosine of u times sine of u plus 1. Okay, this is the order they want us to do things in. And then it says the fraction from the previous step, this fraction simplifies to this. Why? Well, this is what's happening. On the top you have cosine times cosine. That's what cosine squared is. One of those cosines cancels with one of these, leaving you with just a single cosine term in the top and the sine of u plus 1 in the bottom. Okay, I can put the steps here if you'd like. That's the same thing as cosine squared. And you have cosine of u times sine of u plus 1 on the bottom, if you wanted just to see why it's happening. That cancels with that, leaving you with just negative cosine of u on the top and sine of u plus 1 on the bottom, which is this. What property allowed you to do that? The cancellation property. That's just an algebra property, that when you factor, if you have matching factors in the numerator and denominator, they cancel. Okay. Moving to number 14. Establish the identity. They give you cosecant at the top, cotangent at the top also, minus cotangent, and then cosecant times cotangent on the bottom. Okay, this says write the left side as the difference of two quotients. So they're giving you that common denominator in both of these quotients, and they're asking you to split this up. You split it up at the minus sign. So it's first term over this denominator minus second term over that denominator. So that would look like this. Then it says cancel the common factors from the previous step. Do not apply any trig identity. Okay, so this would cancel with this, leaving you with just 1 over cotan. This would cancel with this, leaving you with 1 over cosecant. The expression from the previous step simplifies to tan minus sine. And tan minus sine, let's see. Some of these got cut off. So choice B. Let's see what the other ones were. It was the reciprocal identity. And choice D was the okay, so what's going on with these, the reason that 1 over cotan is equal to tan and 1 over cosecant is equal to sine is through the reciprocal identities. The 1 over, each one's expressed like that. So that this would have been choice B. Okay, moving to number 15. 15, it says the expression 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta simplifies to which of the following? So here they are not forcing you into a specific order in which to prove these steps, so you pretty much have free reign as you would on a test. I don't want to crush your creativity, so there's some students that start it one way and another student that starts in another way, and as long as you're not going off on some scary tangent where you're introducing 3 extra steps, then it's considered, you know, a viable way to get to the solution. Try to keep it as concise as possible. Don't skip over any steps or I won't be able to follow your train of thought, or you're going to lose steps for missing, you're going to lose points for missing a step. So be careful about that regardless of the approach you take. But this was specifically discussed in the guidelines that were on the first page about how you're going to try and always take 2 separate quotients and bring them together as a single quotient. And the only way you can do that is by getting a common denominator. So common denominator for this particular problem, and I've gone over this technique in a couple of problems, is where you take each denominator and throw it into your LCD. Okay, so I put this denominator in there, this denominator in there. Now I'm not going to multiply it out, although you're going to be tempted to do that because then it won't be good for canceling purposes, which I know we're going to have to do probably somewhere in the problem. So for right now, I'm going to leave it like that, and I'm going to make both of these denominators the same. Okay, they both have to look like the LCD. So make each denominator look like the LCD. In other words, multiply it by the missing factor. Okay, this denominator in the first fraction would need to be multiplied by 1 plus cosine of theta in order to make that denominator look like this LCD, and whatever you multiply the bottom by, you have to also multiply the top by the same thing. This denominator is missing the 1 minus cosine theta. So you'd have to multiply the bottom by that as well as the top. Okay, continuing with that. Okay, so now we're going to pull these both together into a single fraction. I'll continue my work down here. The denominator would now look like this. You'd have a 1 plus cosine theta in both of these denominators and a 1 minus cosine theta. So there's your common denominator. And then the tops are 1 plus cosine theta times 1 plus cosine theta. Plus 1 times 1 minus cosine theta, 1 minus cosine theta. Okay, then we're going to have these two terms canceling out, so you're going to have cosine of theta and minus cosine of theta. Then you're going to have 1 plus 1, so I'm trying to combine like terms, see where cancellation applies. Those two terms cancel, these two terms can be collected. So now you have 2 over 1 plus cosine theta, 1 minus cosine theta. So now look at the answers and notice what you're, where we're at right now versus where you need to get to. Notice that none of these answers are fractions. So what they're prompting you to do is to go further. Let's see what we can get, because you don't see any 1 plus cosine or 1 minus cosine in the answers. So let's see what we can get by foiling it out. These are conjugates. And so if you try to multiply them together rather than using full-on foiling, you can use this shortcut, square minus square, by either looking at this binomial or this binomial as you do the two squares, the difference of two squares. Okay, so this would be 2 on the top. Applying the shortcut to foiling for these conjugates, I'm going to get square the front term, 1. Square the back term, cosine squared. Okay, still I see where I'm at right now, but also see that from these multiple choices that I have, that none of them look like that. So that just means that you're going to either do further algebra or substitution. You only have those two vehicles to transform the expression that you're working with. So because there's squares here, I'm reminded of the Pythagorean identities, namely the one that has cosine squared in it. That one goes like this: sine squared plus cosine squared is equal to 1. However, as I've mentioned in several of these problems, when you do want to substitute, you have to get either the left side or the right side to look exactly like this in order for you to go and plug something in for it. Right now, if I was just to go, let's see, I want my 1 to be positive and my cosine squared to be negative. Right now, cosine squared is positive, but if I pull it to this side, it becomes negative. And it won't be here anymore, so it would be sine squared is equal to 1 minus cosine squared. So just by moving that one term, I get an expression that's equivalent to this, and therefore I may perform substitution. So that's what I'm going to do. I'm going to go from having 2 terms in my denominator to just 1 term, because 1 minus cosine squared is equivalent to sine squared. Okay, getting closer. Also notice that none of these answers are fractions, but we can alleviate that issue in the next step. 2 over sine squared is the same thing as 2 times 1 over sine squared. You can pull out that numerator as a multiplier because it's still equal to 2 over sine squared. However, in doing this, I have a definition for this term right here. The reciprocal of sine, even when it's in its square form, is cosecant, but it's going to be cosecant squared because the sine is in its squared form. So this will be equal to 2 times, this is equivalent to cosecant squared. And now you find your definition. So this problem is the truest form of what you're going to be doing on a test, where you will not be forced into doing the steps in a specific order. I mean, sometimes the order will be obvious. Anything like, you know, if one person starts it one way and one person starts it another way, sometimes they're skipping over steps, but sometimes there is free reign to start it in different ways, and this was a good example of that. Okay, so 2 times cosecant squared would make this the answer. Okay, then moving on to the last couple of problems. Example 16 and 17. So example 16, let's see what they want you to do. Use integers or fractions for any numbers in the expression. Okay, looks like they're giving you, let me see, what have they done here? Multiply and simplify this, and they just want to know what it's equal to. So we're going to go at it in our own way. Now, I think, you know, a natural feeling here is that when you have 2 terms times 2 terms, they're looking for you to FOIL. They want you to FOIL. Now, I've talked quite a bit about multiplying conjugates and the way that you could just go square minus square to cut out 3 of the steps. Same thing here. This also happens to have a shortcut. Here you're multiplying a binomial times the same binomial. And anytime you're doing that, you're squaring. It's the same thing as saying, hey, I'm going to take 2 terms, whether they have a plus sign or a minus sign, irrelevant. Just all you do is square the first term. You multiply these 2 terms, even if they're trig words, you multiply those 2 terms and then double the coefficient. This is 1 times 1 is 1, but then you double it. And then you square the back term. Okay, the two terms that came from being squared, they're both positive because you can't square and get a negative. And this term will have the sign of the middle term, it'll be the sign in between the 2 terms. So if you had x plus y squared, now this is from algebra, but you're using all your algebra here. It's just square, multiply the 2 terms within the parenthesis, but then double it, give it the sign that's in between them, and square that back term. Okay, this is the square, double, square shortcut. It is for whenever you are squaring a binomial. Whoops. This is for squaring a binomial. And it's just a shortcut for FOILing. Just like square minus square is a shortcut for FOILing. And at this point in the game, you need to start using the shortcuts that were really introduced in MAC 1033. But you start to realize that there's so much else to do in the problem that you better use the shortcuts whenever you can. Okay, so we're going to try and use that shortcut to get all of that FOILed out. So let's see, you can either be looking at this binomial or this one. It really doesn't matter. I'm going to square, double. Okay, looking at this term right here and squaring it. And why don't we do all of our work off to the side and then just bring our final answer to this blank spot. Okay, so if I was to square this term, I would have cosine squared. Then if I was to multiply these terms, I would just put them right up against each other. Cosine times sine. The coefficient that they would have had if I just multiplied each of their coefficients would be 1 times 1. But you're doubling that, so it's a 2. The sign of this middle term is whatever the sign is that's in between the 2 terms. And then square again, but this time square the back term, which was sine squared. I believe that in addition to the FOILing that I just did by shortcut, there is a minus 1. Okay, then the bottom is just sine or cosine, and it's still quite a mess. So we're going to keep working on this to simplify it. Okay, so let's see. I noticed that we have cosine squared plus sine squared, and that's equal to 1, but let's rearrange things here. We've got cosine squared plus sine squared. We have this minus 2 cosine, and then we have a minus 1. I'm going to put the minus 1 right here because this is 1 minus 1. Minus 2 cosine theta sine theta. And I'm doing nothing with the bottom right now. I'm just working on the top. Okay, so all of this is equal to 1. Cosine squared plus sine squared, we use that in several problems today. That's equivalent to 1. 1 minus 1 cancels. So all of that canceled with this negative 1. They're gone. All you have left is negative cosine, negative 2 cosine theta times sine of theta. And on the bottom, you have sine of theta times cosine theta. Okay, this cancels with this. Sine of theta cancels with that. Things cancel when they're in their product form. So all that's left is negative 2. Well, that's your final answer for this problem. Started off with something very involved and simplified it all the way down to negative 2. Okay, last problem. Establish the identity. They're trying to get you to FOIL again, and once again they are trying to get you to square. We will be using the shortcut that I mentioned right up here. They really try to get involved with those shortcuts. So anytime you're squaring something, whether it has a minus or a plus in it, you're going to use square, double, square. Okay, that's what's going on. Now when they presented this problem to you, they didn't put a little square on it, but you know basically from your knowledge of what squaring is that it's just when you multiply anything times itself. So this was something that was being squared. Here they start you off with the little square, but regardless of whether they start you like this when they're showing that a binomial is being squared, or whether they start you like this, you can use square, double, square. Okay, so here we go. We're going to square this first term, which would be 49 cosine squared theta. Okay, now we're going to go for the doubling part. The doubling part consists of and you should really be using your pencil when you take notes, so just you can see what's going to happen here. You're going to multiply these two things first. 7 times negative 2 is I'm going to erase in a minute, is negative 14 cosine times sine. You're multiplying this term times this term. The coefficients as well as the trig words. But then you are doubling that coefficient. So when you double that 14, it's 28. Okay, there's the doubling part. And some people will do that in their head. They'll just go cosine times sine. This times this is 14. The double of 14 is 28. So it's up to you how much you want to write. Okay, square one more time. Remember, it's square, double, the product, square. This time we're squaring this back term. So positive 4. When you square negative 2, you get positive 4. And then when you square sine, you get sine squared. Okay, there's a lot going on here. So that's what I got from the first parenthesis. You can keep it in parentheses or take it out because there's a plus sign between them, so no need to worry about switching signs. But I'm going to just leave them in there. Okay, now I'm going to do it again. I'm going to do square, double, square again. Okay, squaring this first term. Square the 2, square the cosine. And you would get 4 cosine squared. Multiply these two, which would put cosine right up against sine. You'd have 2 times 7 is 14, but then you double that. And it would be positive 14. So you double that 14 and you get 28 cosine times sine as that doubling term. And then the last thing would be that, now we're trying to prove that all of this on the left side is equal to 53. So we're going to keep going with this. And then, so I did square, double, now square this, and that's 49 sine squared. Okay, so still not doing anything on the right, just working on the left. Now let's see if we can combine like terms here. We have negative 28 cosine times sine, and we have positive 28 cosine times sine. So this, if I combine it with this, they cancel. And then what we have here is we have 49, these are the terms that are left, 49 cosine squared theta, that's that term, plus 4 sine squared theta. And then, let's see what else. Then we have 4 cosine squared theta plus 49 sine squared theta. Okay, and then let's see how we can arrange things to get a 53. So if we were to do, let's see, we could go on our cosine terms, we could go 49 cosine squared theta plus, what else has it? You know, we could try doing this. I think this will work. 49 cosine squared theta plus 49 sine squared theta. I'm just going to group the two terms that both have the same coefficient so that I can factor out greatest common factor. Then as far as the ones that have the coefficient of 4, I could go 4 sine squared theta plus 4 cosine squared theta. 4 sine squared theta plus 4 cosine squared theta. Then I can look at these two terms and they're forcing us to do it a certain way. Okay, you can see I just like to go free range, but okay, let's see if we can stick it into their mold. Okay, rewrite the left side by removing the parentheses. Okay, so if we were to fill in this very first blank spot doing what they asked us to do right here, rewrite the left side by removing the parentheses, we would have we had, okay, so if we did what they said there, rewrite the left side by removing the parentheses, we would have, so that means they want us to clean it up as much as possible. So I have all of this right here. And if I clean it up and deliver it right to this parenthesis, it would be, I was getting ready to jump into the next step already, but 49 cosine squared and then another 4 down here, that would be 53 cosine squared, just combining like terms so I can deliver the most simplified version of what I did get when I removed the parentheses by doing square double square. That's how I removed the parentheses, because foiling it out by square double square allows me to get individual terms that can then be combined as long as they're like terms. So far I got rid of the negative 28 cosine theta sine of theta and combined it with positive 28 cosine sine theta. Got rid of those, simplified it a little bit, and now I'm just collecting like terms. I'm taking my two cosine squared terms, so I didn't really have to do this step right here, but it's written, so I'm not going to bother to erase it. All I did is rearrange things here, but to give the cleanest version of what goes here, I'm going to combine like terms, and I see that I have cosine squared, 49 of them here and 4 of them here. That's 53. Same thing for the sine squared term. I have 49 here and 4 here. That's 53, so that will be acceptable for this answer blank. Okay, then the next thing that they want us to do is rewrite the expression found in the previous step right there by combining like terms. Ugh. Okay, so I've already done that. All right, so if they wanted that here, sorry about that, but it's hard to know what they want in each blank spot. But with these examples, it'll save you from going too quickly. So what I could put in this blank is what it looked like before I combined all my cosine squareds and all my sine squareds, because here they wanted you to combine like terms. So if you're writing what you got originally, that would be everything that we got right here. Which would be 49 cosine squared just looking at this step right there, plus let's copy that right there. 49 sine squared plus 4 sine squared theta plus 4 cosine squared theta. So I guess that's what they just wanted, the terms that I got right there before you combine like terms. And then in this step it said combine like terms, and then you take it to there. Then for your last step it says rewrite the expression found in the previous step by factoring out the common terms. So at this point, what's common to both of these is the 53. So this can be written as cosine squared plus sine squared. Okay, the expression from the previous step then simplifies to 53 using what? They want to know what property. Well, the way that you can turn this into just 53 is by noticing that cosine squared plus sine squared is equal to 1. That would take you to 53. You would replace this by way of the Pythagorean identity, that one that goes like this, cosine squared plus sine squared, or you can write sine squared first, doesn't really matter. That all of that is equivalent to 1. So when you're recalling this Pythagorean identity in order to do a substitution, that would be the reason for why this equals this. Okay, and that completes everything in section 7.4.